If everything is made of atoms, what are atoms made of? What makes up you and me? What are things that matter made of? What is matter made of? It turns out that this question is not new, and most of us do probably know the answer already. From Dalton's theories to Rutherford's models, from Agarwal's hypothesis to Moseley's tables, for all that we learnt and gathered, we can conclude that all life on this planet, you and me, we are nothing but a combination of carbohydrates, proteins and fats, which in turn are polymers of carbon, nitrogen, hydrogen and oxygen. Everything that we see around us is made of one or the other element of this table, and for every element in this table, there is a unique atom which has a fixed number of protons, neutrons and electrons, and these fixed numbers define the identity of the atom and thus the element and everything in the universe. Before we begin any further, I would like to give you a brief idea of the first answers that we humans thought of. It was 2500 years ago when an ancient Greek philosopher, Democritus, formulated the atomic theory of the universe. He was the first person to coin the word atom, the Greek substitute for which is atomos, meaning indivisible. And he proposed that everything in the universe is made up of small indivisible particles called atoms. Now I hope you remember playing with these Lego bricks in your kindergarten. We make a house or something by putting each of these bricks together. Democritus proposed that everything in the universe is nothing but different kinds of atoms put together in a similar fashion. Fast forward to the 1950s, we had already discovered atoms, protons, neutrons and electrons, and everybody was pretty happy with the progress science had made so far, especially in the past few decades, thanks to theories of relativity. But meanwhile in Switzerland, something suspicious started happening. In the early 1960s, things started becoming quirky, or maybe quarky. The European Organization for Nuclear Research, more famously known as the CERN, is located on France-Switzerland border and operates the world's largest particle physics laboratory. And you know what's the most exciting thing about the CERN? It houses the world's largest particle collider, the Large Hadron Collider, or LHC for short. And if I may tell you, the LHC is the highest energy particle collider that humans have ever built. So for those of you who are not much into this, what they do at the particle accelerators is that they propel charged subatomic particles like protons and electrons to very high speeds and energies while containing them in well-defined beams in circular orbits and then smash them head-on, splitting the subatomic particle. In 1964, two physicists at CERN independently proposed the existence of particles known as quarks. Physicists Murray Gell-Mann and George Zwick were working independently on a theory for strong interaction symmetry in particle physics. And their proposition of quarks was verified by the deep inelastic scattering experiments at the Stanford Linear Accelerator Center in 1968. That being said, the LHC with other particle colliders has so far discovered 17 particles, the latest addition being the Higgs boson, which was discovered by Higgs. Its existence was confirmed independently by the Atlas and CMS at the CERN. What are Atlas and CMS? These two are the most powerful particle detectors that are equipped on the LHC to observe high-energy particle collisions. In simple words, when two fast-moving particles at the LHC collide, the Atlas and CMS act like cameras to help study the collisions. And you know these 17 particles that I told you about a while ago? They are the ones that make up the standard model of particle physics. This model is divided into two groups with 12 fermions and 5 bosons. The fermions are the building blocks of matter. There are 6 quarks and 6 leptons, as you can see. The electrons, muons and neutrinos make up leptons. As the fermions make up the matter, the bosons are responsible for interaction between matter. They carry 3 of the 4 fundamental forces in nature, namely the weak nuclear force, the strong nuclear force and the electromagnetic force. The strong nuclear force is carried by the aptly named gluons. It holds quarks together to make protons, neutrons and more exotic particles. The weak nuclear force is involved in radioactive decay thanks to W and Z bosons. Finally, the electromagnetic force is carried by photons. Not only is it responsible for electricity and magnetism, but also for holding atoms together and preventing us from walking through walls. Or is it? The fourth missing force, that of gravity, if you call it a force, is not predicted by the standard model. People have theorized the existence of a particle called graviton, which might be responsible for the existence of gravity, but no such particle has ever been traced by the LHC. Some people say that at the atomic scale, the gravitational force is so weak that it can be ignored in almost all cases, which is true. But there are others who say that not providing any answers for the existence of gravity is just a shortcoming of the standard model. Who knows? This leaves us with the last boson, the Higgs boson. The Higgs is the most mysterious and astounding particle of the standard model. It's often called the God particle and is believed to be the gateway between matter and dark matter. But seize your breath. The Higgs will be discussed in a later video. This might sound like a complete introduction to the standard model, but there's more. For some strange and unknown reason, nature just chose to create an anti-counterpart for every fermion. Quarks got the anti-quarks, electrons got positrons, and neutrinos got anti-neutrinos. So the antiparticles with gluons to hold them together are believed to make up the antimatter, so to say. I know it's a lot to take in at once, but bear with me for a while. The dots are gonna connect very soon. Let us stick to the original question that we had. What are we made of? The standard model tells us that everything is made of these leptons and bosons and their anti-counterparts. It's a very nice and comforting picture. It's a picture that's taught to us in schools, and it's a picture that's taught to students even in undergraduate university. But there's a problem. The problem is, it's a lie. Because if you think about it deeply, the spirit of this answer is exactly the same as of Democritus and his Lego bricks. It's told in schools and colleges because students aren't meant to be exposed to difficult truth too early on it. Also, it makes it easier to learn if you believe that these particles are the fundamental building blocks of nature. But it's simply not true. It's worth stressing, kind of astonishing, and we sort of take it for granted because we don't really think deeply about things that we learn in school. And the thing is, everything that we can and cannot see in the world, all the diversity in the natural world, you, me, and everything around us, we are not just the same 17 particles with slightly different arrangements repeated over and over and over and over again. These 17 particles are not our Lego bricks. The idea of discovering the fundamental particles on the smallest scale will just not work. Because every other day with more advanced machines, we are bound to discover a particle which is smaller than the already discovered ones. And to tell you the truth, the best theories that we have of physics do not have particles underlying them. In fact, the very best theories that we have of physics do not rely on particles at all. They tell us that the fundamental building blocks of nature are not particles, but something much more nebulous and abstract. The fundamental building blocks of nature are fluid-like substances that are spread throughout the entire universe and ripple in strange and interesting ways. That's the fundamental reality we live in. And we have a name for these fluid-like substances. They are called fields. You are already familiar with some fields. When you hold two magnets close together, you can feel their attraction or repulsion before they even touch, an interaction between magnetic fields. Likewise, you know when you jump in the air, you are going to come back down. That's because you live in Earth's gravitational field. So what exactly is a field? Well, a field is something that is spread throughout the universe. It can take a particular value at every point in space. Moreover, that value can change with time. A good picture to have in mind would be of some fluid that ripples and waves throughout the universe. And the origin of the concept of fields was not easy for humans. It all began with Michael Faraday's genius intuitions of electromagnetic waves. He was the man who first thought about how electric and magnetic phenomena work. This intuition is what we now call as electric and magnetic fields. What he envisaged was that threaded everywhere throughout the universe were these invisible objects called electric and magnetic fields. Let me stress, it's one of the most revolutionary abstract ideas in the history of science that these electric and magnetic fields do exist. This might sound very simple now, but it astounded the audiences in the 1800s. And we are used to these things nowadays. You pick up your cell phones, tap a few buttons, and you can call somebody on the other end of the earth within seconds. It's the same principle, first demonstrated by Faraday, that the field is real. You can communicate using the field. And it turns out that the idea of fields was probably much more important than Faraday himself had realized. The realization came about in 1920s when we understood that the world is very different from the common sense ideas that Newton and Galileo had handed down to us centuries before. People like Heisenberg and Schrodinger had realized that on the smaller scales, on the microscopic scales, the world is much more mysterious and counterintuitive than we ever imagined it could be. This, of course, is the theory that we now know as quantum mechanics. And one of the fundamental principles of quantum mechanics laid down by its father, Max Planck, is that energy isn't continuous. Energy is always parceled into some discrete lumps called quantum. See, so far so good, but the real fun begins when we take these principles of quantum mechanics, which say that things should be discrete, and combine them with Faraday's ideas of fields, which propose pretty much smooth continuous objects waving and oscillating in space. The idea of combining these thoughts together is what we call the quantum field theory, and the implications of this theory are far more than enough to fascinate you and me. The universe is full of fields, and what we think of as particles are just excitations of those fields, like waves in an ocean. An electron, for example, is just an excitation of the electron field. Similarly, the Higgs is an excitation of the Higgs field. This may seem counterintuitive, but seeing the world in terms of fields actually helps make sense of otherwise confusing facts of particle physics. For example, when a radioactive material decays, we think of it as spitting out different kinds of particles, right? Neutrons decay into protons, electrons and neutrinos. Now think about it, these electrons, protons and neutrinos are not hiding inside the neutrons waiting to get out, yet they appear when the neutrons decay. How? If you think in terms of fields, the sudden appearance of new kinds of particles starts to make more sense. The energy and excitation of one field transfers to the others as they vibrate against each other, making it seem like new kinds of particles are appearing. Thinking of fields provides a clearer picture of how scientists are able to make massive particles like Higgs boson at the Large Hadron Collider. The LHC smashes bunches of high energetic protons into one another, and scientists study those collisions. See, the thing is, nobody can tell the exact answer. Nobody knows what we are made of. There are always new theories coming up that crush our previous thoughts and frame a new way humanity thinks. But so far as we have researched, so far that we have understood our universe, this is what we conclude. Yes, we are made of elements. Yes, we are made of molecules and atoms. Yes, we are made of electrons and quarks. But they are not the little balls that they are usually misunderstood to be. They are manifestations of waves. An electron is a result of a ripple in the electron wave. So is the case with every particle of the standard model. We are made up of waves. I know it's really difficult to digest. One reason is it's completely counterintuitive, just like Schrodinger's cat being dead and alive at the same time. Secondly, the idea just doesn't agree with the way we perceive things through our senses. We perceive things to be solid physical objects, and saying that the universe is just abstract waves doesn't sound right anyways. The simple answer to this is, it's not the last theory, it's not the final answer. There's probably never a final answer in science. Newton said apple falls because the earth attracts it by a gravitational force. Einstein said no, gravity isn't a force. The earth warps the space-time around itself, which makes the apple fall. Similarly, George Lemaitre proposed the Big Bang theory as a possible answer to the origin of the universe. But we are not sure of it yet. Experiments in the last few years look backwards in time towards the Big Bang, giving us some understanding of what was happening in the first few fractions of a second after time itself started to exist. To look further deep, we launched the James Webb Space Telescope, 100 times more powerful than the Hubble, as you might know, on December 25, 2021. And now we can expect many theories to be modified and several to be discarded and replaced altogether. See, you and me will cease to exist someday, but the urge to satisfy curiosity shall never stop until we know the ultimate answers. Thanks for watching.